Hi there, I hope everyone's doing well. Welcome back to statistics class. This video is going to work a little bit different than some. There's a handout that has a table at the top of it that I'd like you to either print out or download or in some way have available. And at several places during this video, I'm going to suggest you pause things and take a look at some of the problems on there, and then probably follow along as I go through the answers. So the topic of Chapter 9 is correlations. And I pointed out in the previous video that a correlation is just a relationship between two variables. Technically, what you're seeing is that as one thing goes up, the other changes in a predictable way. You can see if one thing goes up, does the other one mostly go up, or does the other one go down? There are two main types of correlations that we typically look at. They're called positive and negative correlations. In a positive correlation, when one thing goes up, so does the other one. You have a scatter plot that would look something like what you're looking at here, where you can see an upward trend as you go from one place to another. One example of a positive correlation would be the cost of using a computer printer and how many pages you print. The more pages you print out, the more it's going to cost to use that printer. Another positive correlation would be the number of free throws a basketball player makes and the number of times that that person is fouled. I've had people point out before that if you're fouling at the end of a game, you're supposed to foul the guy that can't shoot free throws well, and that's certainly true. But if you're not fouled, you're not going to have any chances, and the more chances you have, the more times you're eventually going to make a shot. So yeah, as the fouls go up, the number of free throws is going to go up too. We also have negative correlations, and the idea of a negative correlation is things are going in opposite directions. When one thing increases, the other one's going to decrease. If you had a scatter plot like we were looking at in the other video, the general trend is downward as you go from left to right. Something we see here in Iowa that's a negative correlation is the number of acres planted to different crops. Right now, corn prices are down, so the number of acres planted to corn is going down, but that means that acres in beans and other crops will be going up. They're going in opposite directions. Here's a couple of other negative correlations. If your power in a microwave gets more and more, it's going to have more power and heat up things in less time. I have the number of checkouts open at Walmart and how long it takes you to check out. When they've got lots of checkouts, you check out quickly. When they don't have very many checkouts, it takes a long time. It is also very possible to have no correlation. My first example here is college students' height and their grade point averages. I can remember a few years ago when I had the Kolash twins in this class, and they tried to convince me there must be a positive correlation between height and grades because they were tall and they figured they had to do well. But really, there's no correlation at all with those. Another place where there'd be no correlation is the outside temperature and how many problems you're assigned in a class. I'm sure you hope that as the temperature goes up, you're not assigned any more problems in any of your classes. If you go to that handout I was talking about, you'll see a section that starts off with types of correlations. And I want you to take just a minute now and see if you can go through those problems and see what type of correlation each one is. This would be a good place to pause the video and take a look at those problems. I'm going to go through these, and it does turn out some of these are much easier than others. One of the hardest ones on this section is the very first problem, where it says the grades people got on test 1 and the grades they got on test 2 in stats class. The right answer for that is a positive correlation. And what that means is that the better you did on the first test, the better you probably did on the second test. The people that did well the first time also tended to do well the second time. The people that struggled a little bit on the first test also tended to have the lower scores on the second test. Now, that's by no means a perfect correlation. There certainly are people that did well on one and not as well on the others, but the general trend was high on one, went with high on the second, lower on one tended to go with lower on the second. The rest of these are much more straightforward. Number 2, how much homes cost and the size in square feet, that one is definitely a positive correlation. If you pay more for a home, you're going to get bigger homes. The third one, the outside temperature and sales of hot chocolate at a restaurant, we had a very similar problem on those examples last time. It was about coffee instead of hot chocolate, but the idea there is that as the temperature goes up, hot chocolate sales will go down, and that makes it a negative correlation. Number 4 is also a negative correlation because if you have a more powerful car engine, your gas mileage is probably going to go down. That's a negative correlation. Last one, how many times people shower per week and the magazines they subscribe to. I think the best answer for that is 0. There's really no relationship at all. Continue over on the next page, number 6, it talks about the number of street lights in a neighborhood and the number of crimes committed in that neighborhood at night. Years and years ago, when I was a student at UNI, I was part of the student government there, and one of the things that I am proudest of that we did is we were able to increase lighting on the UNI campus, and we did that by showing exactly this relationship that if you have more streetlights, there's fewer crimes. We actually got the lighting increased after there had been a number of rapes on campus at UNI, and it did turn out that after increasing the lighting, those went down. That's a negative correlation because as one thing goes up, the other one goes down. How tall people are and how much they weigh was another of the examples that came up in the graphs we looked at last week. That one's definitely a positive correlation, not a perfect one, but as one thing goes up, the other one goes up too. Person's income and how likely they are to be audited by the IRS, people aren't always entirely sure of. In the real world, though, that is a very strong positive correlation. Wealthy people are much more likely to be audited than poorer people. And there's a lot of good reasons for that. Wealthier people, they have more money that the IRS can take if they find something wrong. And what's more, they also have way more complicated taxes, so they're much more likely to have problems with their taxes just because there's more things that can go wrong. Number 9 is a problem that years ago I put on a test and I ended up regretting it. It says the balance in a person's checking account and how far the person drives to get to work. When I wrote that question, I intended the answer to be 0, that there really wasn't much relationship between it. But when people did that problem, I had people that very legitimately came up with both positive and negative as answers. The people that said positive, what they were thinking is that if you drive a long ways to work, the reason probably is because you can get a better job. You guys know there's people in Algona that work in Forest City and Mason City and Fort Dodge, and they do that because they can earn more. When I was a kid, we lived in Mount Pleasant. My dad drove about 45 minutes to get to Fort Madison every day because that was where there was a better job. So yeah, that would be a positive correlation. You drive further, you make more money. But there were also people that said, well, if you're spending all your money on gas driving places, then you don't have much money in your bank account. That would be a negative correlation. When I did put this on the test, I ended up throwing the question out because you could legitimately justify just about everything. And the last one, how much a store charges for a product and how much they sell in a day, that's a very classic example from economics. When the price goes up, you tend to sell less. When the price goes down, you tend to sell more. You could look at prices just in stores around here, or especially like the price of gas. Gas has been plummeting in price this year, and people don't care as much about whether they're going to be driving distances. On the other hand, if it shoots back up to $3 a gallon, you may end up watching how much gas you buy and buying less. That would be a negative correlation. Back to the main explanation. The next key thing that comes up is the fact that just because there's a correlation between things, it does not mean that the first one causes the second. And that really is kind of important. You'll often hear studies reported on TV or see people on the internet that are saying one thing causes another. And it's all but impossible to show with statistics that there's a cause and effect between anything. You can show that there's a relationship, but you can't say one thing causes another. That's because a lot of the time there's something else that could be affecting both things that's not one of the things you're studying. We call that a lurking or confounding or extraneous variable, something in the background that changes both of the things we're looking at. A real classic example that comes up almost every time people talk about statistics is the fact that it's been shown that there's a strong correlation between children's shoe size and their vocabulary, which sounds like having bigger shoes must cause kids to know more. So you should put all your kids in like clown shoes and that would be a good thing. But big feet isn't what's causing kids to have a bigger vocabulary. Really going on is you've got another variable, which is age, that affects both of those. As kids get older, they wear bigger shoes and they also know more words. And because of that, that lurking variable here is going to be age. Here's an example that comes straight out of your book. It says, over the past 30 years in the United States, there's been a strong negative correlation between the number of infant deaths at birth and the number of people over age 65. Is it a fact that people living longer is causing a decrease in infant mortalities? Well, no. And then they go into the second part, what lurking variables might be causing the increase in one or both of those variables. Well, the idea here is that we have better medicine in general, and what that's doing is it's causing people to live longer, and it's also causing fewer babies to die. And so, as our science, as our medicine improves, you have changes in both of those things, but the fact that there's more old people doesn't mean that there's going to be fewer babies dying. I mentioned in the last video that you can show correlations using a scatter plot. It's just literally a graph of all the points that make up that relationship. In a positive correlation, the general trend of the graph is up. In a negative correlation, the general trend's down. It's basically like the slope of the correlation. In strong correlations, the dots are packed close together and almost in a straight line. In a weak correlation, they're basically all over the place. If you had a perfect correlation, all those dots would literally be lined up in a straight line. And if there was no correlation at all, they would be all over the place with no pattern to where they were. Now in this class, what we're looking at is what we call linear correlations. And that means we're looking at patterns that are close to being in a straight line. There's lots of patterns that don't make lines, though. What you're looking at in the picture is a sine wave, and that happens when you have things that have a cyclical pattern. For instance, you might have temperatures are higher in the day, lower at night, higher the next day, lower the next night. They keep going up and down. That's a pattern, but it's not a line. You could also have a quadratic correlation like this. It makes a parabola, and what you have is half the time it's going down, the other half it's going up. What we say from our point of view is that overall there's no correlation, or at least no linear correlation in this situation. How strong a correlation is can be measured using a statistic called R. R is the correlation coefficient, and it will always end up being a number that's somewhere between -1 and 1. If you have a negative correlation, you're going to get a negative value for R. If you have a positive correlation, you'll get a positive value, and it will always be somewhere between -1 and 1. If R was 0, we would say that there is literally no correlation. If R is 1 or if R is -1, you'd have a perfect correlation. A perfect positive correlation, R would be 1, have a straight line where everything's going up from left to right. If you had r equals -1, you'd have a straight line going down from left to right, and it would be a perfect negative correlation. Most of the time, though, r isn't 0, and it's not 1 or -1. What it's going to be is a fraction or a decimal that's somewhere in the middle. There's no magic rule on how to interpret how strong a correlation is, but a lot of times what we'll say is if you have a fraction that's bigger than a half or bigger than 0.5, we'd call that a strong correlation. And turning that around, if it was less than a half or less than 0.5, it's going to be a weak correlation. Now, again, there's nothing magic about those numbers. Sometimes I've seen books where they will divide things up into thirds and they'll talk about weak, medium, and strong. And that's perfectly okay as well. But the idea is the closer you get to 1, the stronger the correlation is. The closer you get to 0, the weaker it is. If you have negative correlations, it's close to 0 and close to -1. So here's another good place to pause the video. Most of the problems coming up, they're pictures that you've seen before and you had to describe the type of correlation, but now it's also asking you to estimate a value for R. And if you think about what we just said about strong and weak, that gives you an idea of what you can do with these. We'll look through this section and then a couple of other problems after that once you get back. Well, here's those problems, and I can look at number 11 and tell right off that it's a negative correlation. And it's actually a fairly strong negative correlation. Now, there's no hard and fast answer of what would be the value for R. If I were doing it myself, though, I would probably say something like -0.8 or -0.9. It's a pretty big negative number, and again, the biggest you could have would be -1. Number 12 is a perfect positive correlation, and that would be 1. Number 13, when I look at that, I don't really see any pattern at all, so I would probably put 0 and say that there's no correlation. Number 14, it's a positive correlation and not a terribly strong one. Now, I will tell you, if you can see the pattern, it's going to be closer to a half than it is to 0. And in reality, this might be 0.4 or 0.5. It might even be 0.6, actually. But it's way less of a correlation than what we had on number 11, and that's why it would never be anything close to like 0.8 or 0.9. Again, somewhere around 0.5 is probably a pretty good answer for that one. 15, half of this goes down, half of it goes up, and that's why the answer is going to be that there really is not any linear correlation. I just say no correlation. And if I were to put an R value, it would be 0. Basically, the left side is negative, the right side's positive, and they cancel each other out. And on number 16, it's a negative correlation. It would actually be a stronger correlation than what you have on number 14, but not nearly as strong as what's up on number 11. And that's why I'd probably say something like 0.7. It would be -0.7, actually, if I had to pick a number for this one. There are a couple of other questions that came up on the worksheet right after those patterns of dots, and I'm just going to go through those real quickly. The first one says, how would you report the findings of a study that had a linear correlation of -1.34? Well, I would say somebody screwed up, because that's impossible. The R value has to be between -1 and 1, and this is less than -1, so it can't happen. The second one says, well, what if you got a linear correlation of positive 0.3? I would say it's a pretty weak positive correlation. It is a positive correlation, but it's not really all that strong. There's a relationship, but there's probably more difference than there is a good relationship between your variables. And the last one there says, explain how you could have a correlation coefficient of 0 when the data shows a definite pattern. Well, this is one of those where you've got a pattern, but it's not a line. And you might have something like that sine wave I used as an example earlier, or it could be like number 15, where we have what's called a parabola, where it both goes down and up in the same picture. Either of those would be a good example of something where it would be 0, but you do have a definite pattern. There is actually another way that you could get that, and that's if you had either a horizontal or vertical line. Either of those would also end up having a correlation coefficient of 0. So next up, we're going to talk about how to find R on your calculator. And the first thing that we need to talk about is something that you've got to do, but it always seems kind of weird to do it. You want to, before you do anything else, go to your calculator and hit second and the 0 key. This will even be true if you downloaded a calculator to your computer or phone. You've got to basically tell the calculator that you want to be able to find R. So you hit second 0 and you get into what's called the catalog. And what you're going to do is scroll through all of this big long list of all the different things your calculator can do until you get to a choice that says Diagnostic On. You scroll all the way down to the D's, find Diagnostic On, and then you're going to hit Enter when you get there. Actually hit Enter twice. All it does on your screen is it says Done, and it doesn't look like you did squat, but if you don't do that, your calculator is never going to tell you what R is. And so that really is important. Go to second 0, scroll down to Diagnostic On, and hit Enter twice. Once you've done that once, that'll be stuck in your calculator forever, and you don't need to go back and worry about it changing, but you do have to do that once before you do any of the problems we're going to look at. So then, once you've done that, you're going to actually next go to Stat Edit to your lists like we've done before. And what's going to happen is you'll have pairs of data. I'll show you an example of that here in a second. You want to put the first variable in list 1 and the second variable in list 2. And of course, we talked about putting variables in lists clear back at the beginning of the semester. It is important that you pair up the things so that they're together. This is actually the next problem in that worksheet I've been going through. And you can see that what I did is I went to Stat, Edit, and in list 1, I put all the numbers of children that these families had. Like you can see the last few of those, I had 4, 2, and 3 children. Basically, I'm copying the list, but I'm going down instead of across. List 2, I put the number of doctor visits that each family had. Like the last 3 numbers there are 10, 2, and 9. And again, I just put the entire list of children, the entire list of doctor visits, and I've got to be careful to make sure that I do keep things paired up. Like that family at the end with 3 children had 9 doctor visits. So I put all of those in there, make sure that both lists are done. Once you've got all the numbers in both lists, you quit out of there. You hit second and the mode key, which is right next to second. And then you go to Stat Calc. Now, where you go is not necessarily where you're going to expect. You choose the choice that says Lin Reg. It's choice 4, and it stands for linear regression. We'll talk about what that means in a little bit. But you want to make sure you go down to choice 4, hit Lin Reg, and then hit Enter until you get some answers. And what's going to end up happening is you'll get a readout that looks like what I have down at the bottom of the screen. Now, if you didn't do that first step I said about putting Diagnostic On in your calculator, it's not going to have the R squared and R at the bottom. And you need to go back and make it calculate things by choosing Diagnostic On. What we care about, though, is down at the bottom of that screen where it says R equals 0.8198. That's the value of R that goes with this problem. And so when it says calculate a value of R, okay, it's like 0.82 would be what I'd probably write down. And we're saying that there's a pretty strong positive correlation between how many kids a family has and how many times they go to the doctor. And just like you can with T and Z, you can do significance tests for correlation, for R. What you're trying to do is figure out whether you have a significant positive or negative correlation. Is it strong enough that it didn't just happen by chance? Now, I'll be honest and say this is just about the least important topic in this chapter, but it is something that we're going to go through, and part of the reason I do make a point of including this is that it shows you a different way that you can do hypothesis tests. When we deal with R, we're not going to find the p-value. We're going to do what's called a classical hypothesis test, where we compare the R we compute with a table. And that's exactly why there's a table that's on the front page of that handout that you were given. What you do is you're going to use that handout to look up a value of R. It's what we call a critical value. The way you do that is you'll find N, which is the number of things that were in your sample. Another way to think about it is the number of pairs of data. The number of points you'd have if you plotted the scatter plot on this. That's what your N is, and you'll put that together with alpha, and it's going to tell you a critical value. It's like a cutoff line that tells you whether R is big enough or not. You can always compute R exactly like we just talked about, where you put your two lists in the calculator and then go to linear regression. There are a lot of times, though, that number is given to you, and what you're actually asked to do is compare that and make a decision. The way that we figure out whether we have a significant result or not is that you want the calculated value to be bigger than the number that's in the table. When you do that, you always compare the absolute value, so if there was a minus on your calculator, you just get rid of it. But if that number is bigger than the table, then you have a significant result. If it's smaller, you don't. And that is sort of the opposite of what we did with p-value. You wanted the p-value to be small. For an R test, you want that number to be as big as it can possibly be, bigger than the cutoff line that's in the table. With that in mind, I want you to look at the next part that comes up in that handout and see if you can figure out what the R numbers are and then figure out whether or not you do have significant results. So here is problem 21. Again, if I want to calculate R, what I've got to do is go to Stat Edit. I put the anger hostility scores in list 1 and those depression dejection scores in list 2. You then go to Stat Calc and go down to linear regression, and here we found that the R is 0.665. What I've got to do now is compare 0.665 to the table, and the way I do that is I look up how many pairs of data I have. There are 8 pairs of data, 8 subjects they looked at, and what we want to do then is to go to that table. It says the 5% level of significance, so if I go to 8 and 0.05, the critical value is 0.71. I compare my calculator with 0.71. This time 0.665 is less than that cutoff line, and that's why in this case, no, there is not a significant correlation. There is a relationship, but it's not strong enough that I can say it didn't just happen by chance. You do pretty much the same thing on number 22. Here I calculated that the R value was about 0.72. This time we have 12 cities, and I go to the 0.01 level of significance. The cutoff line this time is 0.71, and now my calculator is just a little bit more than that, so yes, this would be a significant result. Again, whenever you're doing an R test, you want the calculator to be bigger than the table. If the calculator is larger, then yes, it's significant. If the calculator is less, no, it is not. The next topic that comes up in this chapter is what's called the coefficient of determination. Coefficient of determination is r squared, and you probably noticed a line on the calculator readouts that said r squared. That's literally the number r taken times itself, r squared. And what that does is it tells you the amount of change in the second variable that you could predict from the change in the first one. So if I thought back about that relationship between how many kids a family has and the number of doctor visits they make, this would be the amount of the difference in doctor visits that has to do with how many kids there are in a family. How much of the second one you can predict from the first one. There's like a whole page about correlation and determination on that worksheet. This is another place you might want to pause the video and take a look at those problems. So this first one, it's asking about people's age and their willingness to give out credit card information over the internet. And it tells you that they had a value of negative 0.68 for R. And the first question says, what percentage of a person's willingness to give out their credit card information could be attributed to their age? Well, that attributed to is exactly what r squared is, and that's why what I'm going to do here is take negative 0.68 squared. If you do that, we're going to get about 46%, 0.4624. The second question says, what percentage would be due to other things besides age? Well, if 46% is because of age, then 54% would be because of other stuff. I can always just subtract from 1 or subtract from 100% to get that idea of other factors. And the third one, it says, explain what the negative correlation in this problem means. As older and older people were sampled, what happens to the ratings? Well, remember, a negative correlation says when one thing goes up, the other one goes down. So here we'd be saying as people got older, they were less willing to give out their credit card information. And that would be what our survey is about. Basically the same kind of thing on the next one, where they're looking at how long employees have been with the company and what their level of job satisfaction is. For part A, I took the R value that was given and I squared it, and it's like 0.765625, or about 77%. The amount of job satisfaction that's due to other things, I subtracted from 1 and got about 23%. And since it's a positive correlation on part C, we could say the longer people have been with the company, the better they feel about their job, basically. The long-time employees are going to have more positive ratings than the new ones. Number 25 is almost backwards from the other problems. This time, they're looking at a real study that was done in California where they had people drink more and more, and they wanted to see how alert they were. And here they're giving us R squared. They're saying 50% of alertness could be attributed to the alcohol. That means R squared is 0.5, or 50%. What we've got to do to find R is take the square root. You get 0.707. The second one, where it says explain what a negative correlation means here, well, if you are familiar at all with drinking, you know the more people drink, the less alert they are. And the next couple questions kind of tie together all the different stuff we've talked about. We have this one that talks about the artificial sweetener saccharin. You can still find saccharin in pink packets in restaurants. But not a lot of people use it to sweeten other things today. We've moved on to things like aspartame and stevia and various things like that. But it used to be, back when I was a kid, that saccharin was what Diet Pop and Diet Anything was made with. Here they tell us that 25% of the variation in one thing is due to another, and again we're supposed to find R, so what I did is I took the square root of 0.25, and part A is going to be 0.5. Then they ask you a question about whether this was significant. It says the study involved 24 rats, find a critical value, and it says at the 0.01 level of significance. Well, if you go to the table and you look up 24, you'll notice that the cutoff line that goes with 0.01 is R would be 0.52. The calculated number we got was 0.5. That's a little bit less than 0.52, and that's why no, this was not a significant result. So, yeah, the critical value is 0.52 on part B, and part C, no, it is not significant. How would you describe the correlation? Well, since it's 0.5, that's about as middle as you can get. I'd probably say it's a moderate or medium positive correlation. It actually was reported back in the 70s that saccharin caused cancer, and it says, according to this study, is that a correct conclusion? Well, the answer is no for a couple of reasons. One of them is that they didn't get a significant result, but really more important with that is even if they had, you can't say one thing causes another. There could have been other things going on in the background, and that's why it's definitely not cause that you can say. If you ever see that word cause, like on a quiz or a test, the answer is no. And part F is just sort of a think about it question. It is interesting that lots of different places in the world did ban saccharin, but you actually still can get those pink packets all over America. And sometimes people wonder whether that should be the case. We have replaced it with things like NutraSweet or aspartame. That's actually a sweetener that's been banned in some places too. You can't get NutraSweet in Mexico, for instance. But usually in this country, what we try to do is give people information and have them make decisions, and that's largely what was done with saccharin. Similar kind of question on number 27. Part A, you look up the critical value, and for 20 players, you should end up with 0.44. And because we got a calculated value of 0.43, it's going to end up being no. If it's no at the 0.05 level of significance, it's definitely no at the 0.01 level of significance. This time the critical value is 0.56, and we're still below that. And when you get to part E, what we've got to do is take 0.43 squared. We're basically figuring out that 18% of the difference in scoring has to do with height, which of course means that like 82% has to do with other things, like maybe the player's skill. And the last problem in this section, it talks about the fact that 49% of the variation in gas mileage is due to how much cars weigh. Once again, they're giving you R squared, and what you've got to do is find R, so you've got to take the square root of 0.49, and it turns out R would be 0.7. The last topic that comes up in this section is linear regression. And when you do linear regression, what you're doing is you're using a line to make predictions about what's going to happen when you have two variable data. And what you're essentially doing is sort of finding the average of that data. What's literally going on is if you picture your scatter plot with all those dots showing how when one thing changes, the other one does too. If you drew a line right down the center of where all those dots are, that's the line that is like the average that we're going to use to estimate. You're finding a line that's as close as possible to every single point in that set. You probably know from algebra class that most of the time you write lines in the form y equals mx plus b. Technically, when we talk about a regression line, we usually write it as y hat equals m times x hat plus b. That's just the equation of a line, and you might have actually noticed that when we were finding r before on the calculator, there were a couple of other things that showed up on that screen. It said a and b. All those are the slope and the y-intercept of a regression line. They're basically the m and the b that come up in this formula. This topic also comes up in my math analysis class, and Jack did it in there. He'll remember actually coming up with those regression lines and then plugging stuff into them. In this class, we're not going to actually deal with writing the equations of those lines. What we are going to do is use equations that are given to make predictions. When you work with regression lines, the m, the slope, is telling you the rate of change in one of the variables. So like if you think back to that problem about how many kids families had and how many visits they make to the doctor, what that slope would be telling you is for each additional kid a family has, how many trips to the doctor does that make? The y-intercept is the initial value. That would be like if you had a family that had no kids at all, how many visits are they likely to make to the doctor? Again, what a regression equation really does is it looks at like the average of everything and it makes the best estimate it can based on the data that you're given. But regression equations aren't always totally accurate, and the further you get from the middle, the less accurate they tend to be. Sometimes you can get kind of ridiculous answers. We'll see an example of that here in just a second. So to give you an idea of how you can use a regression equation, we're going to look at this example. It says the New York City Police noticed that as the number of officers on the street increased, the crime rate decreased. And your common sense ought to kind of tell you if you have more cops around, probably there's going to be less crime. Now, the equation I have here is totally made up. It says in a certain precinct there was a linear correlation with the regression equation y equals 135 minus 7x, where x is the number of officers and y is the number of crimes that were committed each day. So if you tell me how many cops there are on the street, I can tell you how many crimes there's likely to be. We're going to look at three questions related to this situation. The first one, it says how many crimes can be expected with 12 officers on the street? So I'm giving you 12 officers. We need to figure out how many crimes. What you do here is basically just plug in 12 for x and see what y is. So 135 minus 7 times 12, we end up with an answer of 51 crimes. That's all I do. The next one's a little bit different question. It says how many officers would be needed to reduce the number of crimes to 20? So if you think about this for a minute, what they're doing is giving you the number of crimes, and we need to figure out how many cops would make that happen. And what you're going to do with this one is to plug in the number we have there, the 20, for y. So I know that 20 would equal 135 minus 7x. We got to figure out x, the number of officers. So you solve an algebra problem, you subtract 135 and you divide by -7, and the answer my calculator says is 16.4. Now this is a situation where you would do exactly like you did back when we were doing those sample size problems earlier. You're always going to round the answer up. The answer that I should actually say here is 17. Because if I only had 16 officers, I wouldn't reduce it quite enough to be down to 20. It would be 20 something, but it wouldn't be exactly 20. If I have 17, it's going to be more than enough. The third question is a lot like the first one, it just has a different number. How many crimes could be expected if there were 25 officers on the street? But if you do plug in for x, you get kind of a weird answer. If you take 135 minus 7 times 25, you get -40. So we have a negative number of crimes. You know, all the robbers are taking the jewels back to the jewelry store and taking the money back to the bank and all of that stuff. So, you know, it really is an impossible answer. And the reason that happens is that 25 is a way bigger number than what would they use to come up with that equation to begin with. So you do get kind of a ridiculous answer. In the real world, since you can't have a negative number of crimes, what we'd probably say is it's essentially 0. There is a regression equation section on your worksheet, and again, we're going to give you just a minute to look through those and see what you can get. So the next problem here, they give us an equation that's supposed to figure out how much a law firm's phone bill would be based on how many long-distance calls they make. And the first two questions, they give you a couple of numbers of long-distance calls. You're supposed to figure out what the bill is. If you look at the bottom left, I did that. I just went to the formula. I plugged in 142 for x, and then I plugged in 25 for x. And the answers to A and B would be $306.41 and then $98.15. So those are pretty straightforward. Plug them in and see what you get. Part C, we have this really stupid question where it says that the firm's financial advisor suggests they limit their phone expenses to no more than $150 a month. Now, if my lawyer cares about how much they spend on the phone, I think it's probably time to change lawyers because they certainly ought to have enough money to pay a phone bill. But since that's what it says, we'll do what the problem's telling us. They're giving me the y. They're giving me that 150 equals 5365 plus 178x. And what I've got to do is subtract and divide. The calculator's answer here is 54.12, which, since I can only make a whole number of phone calls, means they can only make 54 calls. The other two questions are asking you what the numbers in the equation stand for, and I do have a typo in part D. It should say 5365. What that would be is like the base bill. It's what they pay to have a phone in the office even if they never use it. If they make no calls at all, they've still got to pay $53.65 to the phone company. The 178 would be how much they pay for each long distance call that they make. Now, there's really no plans I'm aware of anywhere that charge a flat rate per phone call, but that might be like the average cost for each long distance call. That's a possibility. At any rate, it is like as each call they make, they're going to be spending $1.78 more. And the other problem here, it says to be careful of units of measurement. And what they're telling us is what's going to be the resale price of a car that is a certain number of years old. And the first one is what would you have for a 3-year-old car, then what would you have for a 6-year-old car? Well, what I did here is I plugged into the formula the numbers for X, and you notice the answers I got were 161.14 and 96.58, which if you look at this quickly, you could almost think that that means I could buy a 3-year-old car for $161.14, which isn't very likely. What's really going on here is if you look carefully at the problem, it tells you that Y is in hundreds of dollars. And that's why what I did right below that is I took those answers times 100. And technically the first answer would be 16,114 and the second one is 9,658. Both of those are actually impossibly accurate answers. In the real world, you'd say about 16,000 and probably about 9,600 would be what we'd end up saying for those prices. The third question says, when will the car be worthless? Well, worthless would mean it's worth $0. So what you can do is plug in 0 for Y. And if you do end up solving that, here I actually divided by a positive number, which is why my answer technically shows a negative. But what you would end up getting is about 10.5 years. That's actually, in the financial world, a lot of times 10 years is used for the amount you're allowed to use for depreciation on expenses like a car. And so, yeah, 10.5 years, you would have basically a worthless car. And the last one says, what's the annual decrease in the resale cost? Sometimes I'll have people that will take it between 0 and 10, plug all of those numbers in, and then find the average of them, and boy is that a pain. The answer is $2,152. Basically, it's the slope. It's the number that's by X. What the equation is telling us is that this car initially cost $22,570, and each year it goes down by an average of $2,152. So again, the slope is how much it changes per year. The y-intercept is what the initial value of it was. So that's a lot of stuff, but hopefully it's pretty straightforward overall. There's a couple of things you can do to get a little bit more practice. At the end of that same handout that I've had you go through while watching this video, there's a review section that I'll have the answers to posted online as well. There's also a handout that says correlation review with answers. That's just more ways of practicing the same basic stuff. You obviously will have a quiz this week over correlation, and then next week we'll go on to some totally different stuff. So I hope everybody's doing okay, and have a good week.